Okay, and we're back. I do want to add a little extra layer as well because when we're talking about, yes, we have single, double, and of course triple bonds, then what I'm starting to realize is that I want to talk about rotation around those bonds as well, because when you have a single bond, you have free rotation, right? So free rotation around the bonds, which can allow carbon and things it's attached to have basically a lot of different arrangements. But because they have different arrangements, that also can cause more confusion because you might be thinking to yourself, well, wait a minute, they look like the same exact structure, or they look like different structures, but they actually could be the same exact structure. That's what I'm trying to say. Okay? So with this, you have, again, free rotation, no rotation with something that's linear, no rotation. Okay? And then here, you're going to have restricted rotation. So double bonds, you have restricted rotation. Now, of course, you do see that I have a flashcard moment up here. That means that you want to stop yourself and create some kind of flashcard to help you start understanding bonding properties of carbons, for example. Maybe on the front, you can say carbon hybridization. On the back can be all three of the hybridized amounts. So to kind of help you with that, because yes, it can get messy with me in my brain, I actually am going to go and start to basically write down some details about the different hybridizations that we just saw. Okay, let's go to the next. Again, you stop and make sure we have details down in these hybridizations. We talked about three main ones that help us understand those covalent bonds that carbon is creating, and of course the shapes that come from it. All right, so I'm going to start with the sp3 hybridization. Now, I don't know, let's just make really short portions. I'm going to say, okay, we have a carbon that has 4 things attached to it. We have a carbon that has 3 things attached to it. And what are these things? We know that we're talking about electron groups. So those things can be electron lone pairs. Just write electron groups. Get my head out there. So electron groups, which can be, of course, other atoms, or it can be lone pairs. Let's just get that out of the way off rip. Okay, so of course, the front of the card can be about carbon hybridization. The back would be something like this. It is your choice, but I just want you to be as active as possible in this moment. Okay, let me erase this here. Let's get down to the details. When you have 4 electron groups surrounding the carbon, then you're going to have sp3 hybrid orbitals. Okay, and those sp3 hybrid orbitals are going to have the shape that is tetrahedral. Again, we have a carbon with 2 molecules that are in plane and 2 that are out. Okay, because we are dealing with sp3, we know that they're going to form sigma bonds or just simply single bond. All right, so you can just write that, but let's kind of add an example. Let's say that we have this molecule. And this actually represents a skeletal structure we're going to talk about later on. And as you can see, each carbon, we're not able to see the hydrogens because it's skeletal. It doesn't show hydrogens in skeletal structures. But this organic molecule here has single bonds. There are no double bonds or anything like that. And so these single bonds can rotate around. And because single bonds can rotate, make sure, and they can rotate freely, this structure will be the same as this structure here. They have the same amount of carbons, okay? They have the same amount of carbons, they're just arranged differently. Okay? Let's count the amount of carbons, 1, 2, 3, 4, and 5. The amount of carbons here is still 1, 2, 3, 4, and 5. All that happened is that this carbon 2 here, definitely had it, and carbon 2 and 4 both had different attachments. That's all we're seeing. Okay? Now let's move on and go into the 3 things that are attached to carbon. And what are those 3 things? Again, it's going to be electron groups. Okay? When 3 things are attached, that means we're only going to need 3 atomic orbitals to mix to form sp2 hybridized orbital. Before, we want to go back and make sure that you guys have the 109.5 degree bond angle between these bonds here, these sigma bonds, just make sure that it's that. And also just to add to, yes, they can rotate, but it can, when you actually have carbons moving to other areas and causing extra branching, that could be a completely different structure. So we'll talk about some of the isomers in a moment. All right, back to 3 things for sp2. Okay, so we have these sp2 orbitals, and again, these brand new hybrid orbitals are going to have their own shape. This shape is going to be trigonal planar. Okay? And so that means you're going to have a carbon double bonded, and then you're going to have, of course, 2 other single bonds here. So this double bond here is going to be made of sigma bond and one pi bond. And of course, all these single bonds are all sigma bonds here. All right. Now, a trigonal planar is going to give to be very flat. And so you're just going to have 120 degrees angles, as you see here. And again, you're dealing with sigma and pi bonds to give yourself a double bond. Now, when it comes to double bonds, you do have restricted rotation. And so that means that, yes, it can rotate a bit, but it's not going to be as much. It's just going to be able to rotate here a little bit and kind of change groups that are attached to the carbon itself. So let's go ahead and come up with something here. Like, for example, we have one carbon here and another one here. We have a group here and a group here, right? Due to rotation, say one of these groups rotates, it actually can create brand new geometric isomers, which means same type of actual molecular formula, but their structure is different. So these isomers, as you can see, since both groups are on the same side here, going to be called a cis isomer. And then, of course, when they're across from one another, one group here and one group down here, or, of course, you can have the opposite, one group here and one group here. These are called trans. And so we'll talk about how some of these geometric shapes arise when you have, of course, double bonds that restrict that rotation. Single bonds, free rotation. You can kind of move things around and get all kind of different, like structural isomers, for example. But when it comes to double bonds, because they can only rotate specifically, they're what's called geometric isomers because it's all about the spatial region. All right. Now let's end off with, of course, when you have two electron groups surrounding our overall carbon, you're going to have sp hybridized orbitals, which is going to be linear. And so if I have a triple bond, this is the carbon here, this is the carbon here. There's going to be a 180-degree bond angle and no rotation here. Write that back. Okay, no rotation. And this is kind of how it was set up, or at least start to set up the flashcard. Again, you can edit this, of course, make it look way better than how I'm writing it. But again, this is just getting your brain juices working, making sure that you are staying active. You can add more examples about their orbitals themselves, their angles, their shapes. Of course, give yourself more examples, any options you want. So what else? I mean, yes, we understand that we have our atomic properties. We understand valence bond theory. We're able to see visually how carbon is able to make those stable sp3, sp2, or sp bonds. But what else about carbon makes it so amazing? Well, carbon is actually small. We go back to the periodic table. We said as you go across, you increase electronegativity, and as you go up a group, you also increase electronegativity. Well, you increase atomic size, or you decrease atomic size as you go up a group. And since carbon, when you go back to that actually here, since carbon is right here up on the group, we want to make sure that we understand that carbon is actually very small. And so because it's very small, it's going to allow better overlap. What am I talking about? Well, we know we're dealing with sigma bonds, right, and pi bonds. And so sigma bonds have end-to-end overlap. And when you have better overlap, you have more stable bonds. Guess what? Carbon can provide that because it's so small. All right, it's able to orient better and become more stable. Also, these carbon-carbon bonds that we see here, these carbon-carbon bonds are short. They allow sigma and pi bonds, allowing for more structural diversity. Because they're so short, they can make sigma bonds, pi bonds, etc. More pi bonds, of course, more bonding. You have triple bonds. Of course, if you only have sigma bonds, it's single bonds. And if you have a pi and a sigma bond, you have a double bond here, right? So again, these shorter bonds allow for more diversity. Really, the amount of carbon bonds and their strength are going to really account for catenation, which is all those chains and branches and rings that carbon can form. So when I'm thinking of now catenation and everything, I'm bringing it all together, I want to make sure we're clear that carbon can catenate. They're not just making bonds, they're making stable chains and rings and branches. We'll talk a little bit detailed about that next week.